simple on the surface, but it's actually pretty complex. How fast do electrons really move?
Right, and you've probably heard this idea, maybe you even thought it yourself, that electrons in a wire just zip along at the speed of light.
Exactly. It's a really, really common thought. But it turns out that's mostly a misconception.
Yeah, and the sources we're looking at today really help clear this up. They show that electron speed is, well, it's incredibly varied. It really depends on where the electron is, what it's doing.
Okay, so that's our mission for this deep dive. We're going to unpack these sources, cut through some of that confusion, and show you the surprising range of speeds. We're talking, like, shockingly slow sometimes.
And other times, mind-bogglingly fast. And we'll explore what happens when they get pushed right up against that ultimate speed limit.
We're aiming to give you the real picture, the nuanced one, based on the info you shared with us.
Okay, so where should we start? That big misconception, wires.
Yeah, let's hit that one first. Electrons and wires, speed of light. You flip a switch, the light comes on instantly, so you think, must be fast, right? Light speed fast.
Makes intuitive sense. But the sources, they paint a very, very different picture for the average speed along the wire.
What do they say? How fast is it, really?
It's called drift velocity. That's the technical term for the average speed in the direction of the current. And it is incredibly slow.
How slow are we talking?
Like millimeters per second.
Wait, millimeters per second? That's practically crawling, fractions of an inch per second.
Yeah. It's genuinely surprising when you first hear it.
Okay, then how? How does the light come on instantly if the electrons are moving that slowly? That doesn't add up.
Ah, see, that's the key insight our sources give us. It's not the electrons that travel instantly down the wire. It's the signal, the electromagnetic field.
The field.
Yeah, the wave that tells the electrons to start moving. That propagates down the wire at very close to the speed of light.
Okay, so it's like
Yeah.
nudging the first domino in a long line.
Exactly like that. The fall signal travels down the line super fast, even though each domino only moves a tiny distance.
Got it. So the signal, the push, is fast, but the actual drift of any single electron down the wire is glacial.
Pretty much. Don't confuse the message carrier of the field with the things being carried along the electron's net movement.
Okay. But is that drift the only speed involved? Are the electrons just sitting there waiting for the push?
Oh, definitely not. And this is where it gets even weirder, maybe. While that drift velocity is tiny, the individual electrons inside the wire, they're actually zipping around like crazy.
Zipping around?
Randomly. Bouncing off the atoms in the metal, bouncing off each other. This random motion is related to temperature, quantum stuff like Fermi velocity. And those speeds can be really fast.
Oh, fast.
Like a significant fraction of the speed of light, potentially. Really, really fast. But in all directions, canceling out.
So hang on. Inside the wire, you've got electrons darting about almost randomly at huge speeds. But when you apply voltage, the overall effect, the net movement in one direction, is this tiny millimeters per second drift.
That's exactly it. It highlights how speed isn't just one number here. You've got the fast random individual speed and the slow collective drift speed.
Wow. Okay. That definitely throws out the simple light speed in a wire idea completely.
Yeah. Right.
All right, so they crawl in wires despite buzzing around internally. What about somewhere totally different, like inside an atom, bound to a nucleus? Do they speed up there?
Oh, yeah. Big time. When an electron's orbiting a nucleus, it's a much faster situation.
Faster how?
Well, one of the sources gives a specific example. For a hydrogen atom, the electron is whipping around at something like 2,200 kilometers per second.
Whoa, okay. 2,200 kilometers per second. That's a huge jump from millimeters per second. That sounds seriously fast.
It is. Compared to our everyday experience, that's incredibly quick.
Yeah.
But here's the catch.
There's always a catch, isn't there?
Well, relativity always looms large. Even 2,200 kilometers per second. It's still less than 1% of the speed of light in a vacuum.
Less than 1%. Wow. So even in an atom where things seem pretty energetic, it's still way, way below the ultimate speed limit.
Exactly. Fast, yes, but nowhere near c.
Which brings us neatly to that limit. CC, the speed of light in a vacuum. We keep mentioning it as this barrier. Why? Why can't electrons or anything with mass actually reach it?
That's fundamental physics, straight from Einstein's special relativity. The core idea is anything that has mass cannot be accelerated to the speed of light in a vacuum, period.
And electrons, tiny as they are, have mass.
They do, so they're stuck below c.
But why physically? What stops them? What happens as they get closer and closer?
Well, the sources explain it through this concept of relativistic mass. As something with mass, like our electron, gets pushed faster and faster closer to C, its effective mass actually increases.
It gets heavier the faster it goes.
Effectively, yes. From the perspective of the force trying to accelerate it. And this isn't just theory, it's something measured and accounted for all the time, especially in accelerators.
Okay. So if it gets heavier, it gets harder to push, right?
Exactly. It takes more and more energy to get the same amount of acceleration. To actually reach the speed of light, the energy required would become infinite.
Infinite energy.
Right.
Right. Which we don't have. So the universe basically puts up this infinite energy barrier at C for anything with mass. It's like pushing a car that turns into a mountain as you approach the speed limit.
That's a pretty good analogy, yeah. It's an absolute cosmic speed limit for matter.
Okay. So C is the wall. Where do we get electrons closest to that wall? Where do we see them pushed to the absolute extreme?
That would be in particle accelerators. These are, huge machines built specifically for this purpose. They use incredibly powerful electric and magnetic fields to just slam particles like electrons up to enormous speeds and energies.
And how close do they actually manage to get them? Are we talking 90%, 99%?
Oh, much closer than that these days. Modern accelerators, the sources mention speeds like, get this, 99.999992% of the speed of light.
Whoa. That's a lot of nines.
It is. It's practically at the speed of light from our normal perspective, but crucially, it's still just under. That limit holds.
Okay, that is unbelievably fast. And I bet at those speeds, all that weird relativistic stuff Einstein talked about really kicks in, doesn't it?
Absolutely. It becomes totally dominant. The sources highlight a few key effects you see very clearly.
Like what?
Well, first, that mass increase we just talked about. It's not subtle at these speeds. The electron's effective mass can be thousands, even millions of times its normal rest mass.
Millions of times heavier. Wow. How do the machines even handle that?
Yeah.
Especially the circular ones.
Right, so in synchrotrons, the circular accelerators, they use magnets to bend the beam and keep it going around. As the electrons get effectively heavier, you have to ramp up the strength of those bending magnets precisely to keep them on the right path. It's a major engineering challenge.
So the machine's constantly adjusting for this changing mass. Wild. What else?
Time dilation, that this was always a mind bender.
Time slows down.
For the electron, yes. From our perspective, standing in the lab, time for those super-fast electrons passes much more slowly than it does for us.
So if we could, strap a tiny watch onto the electron?
It would tick much, much slower than the clock on the control room wall. Yeah. And this isn't just theory, it's directly observed, and it's vital for understanding how unstable particles behave when accelerated. They appear to live longer from our point of view.
That's just hard to wrap your head around.
Mm.
Okay, mass increase, time dilation. You mentioned something about circular accelerators specifically, a third effect.
Yes, synchrotron radiation. This is a big one for circular machines.
Synchrotron radiation, what is that?
Basically, when you force a charged particle like an electron to change direction, which the magnets in a circular accelerator are constantly doing, it radiates energy. It emits electromagnetic waves, often in the form of intense light or X-rays.
It loses energy just by turning.
Yes. And the faster it's going and the tighter the turn, the more energy it radiates away. For electrons, which are very light, this is a huge effect at high energies. It means you constantly have to pump energy back into the beam just to make up for these losses.
So it's like trying to drive a leaky car really fast. You keep losing fuel just by steering?
That's a decent way to think about it. It's a major limitation for how high an energy you can reach with electrons in a circular machine.
Which is why sometimes they use linear accelerators instead, just straight lines.
Exactly. Linear accelerators, or linacs, accelerate in a straight path. No bending, so no continuous synchrotron radiation loss that way. They can often reach higher peak energies for electrons because they avoid that specific problem.
So linacs for raw energy maybe, circular ones for keeping things compact, but they have this radiation issue.
Right. Circular machines pack a long path into a smaller footprint, but for light particles like electrons, synchrotron radiation becomes the bottleneck. That's why high-energy electron synchrotrons need to be enormous, making the curves very gentle.
Okay, so this radiation sounds like purely a downside, an energy drain, a problem for the accelerator physicists.
But here's the brilliant twist, and something the sources really highlight. That radiation, that lost energy, it turns out to be incredibly useful.
Useful? How?
The intense beams of X-rays produced by synchrotron radiation are now one of the most powerful tools we have in science. Scientists build entire research facilities called synchrotron light sources around these accelerator rings, specifically to use that X-ray light.
So they harvest the problem.
Precisely. They use those X-rays to study everything from the structure of proteins and viruses to developing new materials, catalysts, analyzing archaeological artifacts, you name it.
Wow, so what started as an annoying energy loss mechanism in one field, particle physics, became a critical resource for dozens of other scientific fields.
It's a fantastic example of how tackling a fundamental physics challenge can spin off entirely new capabilities. The obstacle became the tool.
That's incredible. Okay, let's just quickly pull this all together. We started way down at the bottom with electrons barely drifting in a wire, millimeters per second average speed.
Even though they're buzzing around randomly, much faster inside.
Right. Then we jumped to atoms, where they're much speedier, thousands of kilometers per second, but still, less than 1% of light speed.
Still well within the normal rules, relatively speaking.
And then the extreme end. Particle accelerators pushing electrons to that mind-blowing 99.99% of C.
Yeah, incredibly close, but never quite at C. And that's where relativity really shows its hand. Mass increase, time dilation.
And that synchrotron radiation, the energy lost in turns.
Which, remarkably, we now use as a powerful scientific light source.
This is the big picture here. Electron speed is all over the map. It's not one number. It depends entirely on the context.
Hugely variable, yeah.
Okay.
From a crawl to near light speed. But always, always respecting that ultimate speed limit C for anything with mass.
And pushing things towards that limit is where we really see physics get interesting and where we sometimes turn limitations into advantages.
Absolutely. Confronting those relativistic effects has not only deepened our understanding, but also given us new tools.
It really makes you think, doesn't it? How
Yeah.
sometimes the biggest challenges, the things that seems like roadblocks, like losing energy when you try to steer an electron, can actually hide the key to completely new discoveries and technologies if you just look at them in a different way. That obstacle literally became a source of light for science, something to chew on.